Hello guys, I'm Mikaela. I hope you're all doing well, and today's video is gonna be about mathematics in nature. So have you guys heard about the Fibonacci sequence? If not, then sit back and relax, because you are in for a treat! The Fibonacci sequence is a series of numbers in which each number is the sum of the two that precede it. The famous Fibonacci sequence has captivated mathematicians, artists, designers, and scientists for centuries. Also known as the golden ratio, its ubiquity and astounding functionality in nature suggests its importance as a fundamental characteristic of the universe. The Fibonacci sequence can be found in flower petals, since the number of petals in a flower consistently follows the Fibonacci sequence. Famous examples include the lily, which has 3 petals, buttercups, the chicories 21, the daisies 34, and so on. It is also found on seed heads, because the head of a flower is also subject to Fibonaccian processes. Typically, seeds are produced at the center and then migrate towards the outside to fill all the space. Sunflowers provide a great example of these spiraling patterns. The Fibonacci sequence can be found on pine cones too. Similarly, the seed pods on a pine cone are arranged in a spiral pattern. Each cone consists of a pair of spirals, each one spiraling upwards in opposite directions. The number of steps will almost always match a pair of consecutive Fibonacci numbers. Likewise, similar spiraling patterns can also be found on pineapples and cauliflowers. The Fibonacci sequence can also be seen in the way tree branches form a split. A main trunk will grow until it produces a branch, which creates 2 growth points. Then, one of the new stems branches into 2, while the other one lies dormant. This pattern of branching is repeated for each of the new stems. A good example is the sneezewort. Root systems and even algae exhibit this pattern. Surprisingly, spiral galaxies also follow the familiar Fibonacci pattern. The Milky Way has several spiral arms, each of them a logarithmic spiral of about 12 degrees. Subsequently, after a few rotations, spiral arms should start to wind around a galaxy, but they don't, hence the so-called winding problem. The stars on the outside, it will seem, move at a velocity higher than expected, a unique trait of the cosmos that helps preserve its shape. Both human and non-human abound with examples of the golden ratio. The mouth and nose are each positioned at golden sections of the distance between the eyes and the bottom of the chin. Similar proportions can be seen from the side, and even the eye and ear itself. Even our bodies exhibit proportions that are consistent with Fibonacci numbers. For example, the measurement from the navel to the floor and the top of the head to the navel is the golden ratio. Animal bodies exhibit similar tendencies, including dolphins, starfish, sand dollars, sea urchins, ants, and honeybees. Speaking of honeybees, they follow Fibonacci in other interesting ways. The most profound example is by dividing the number of females in a colony by the number of males. The answer is typically something very close to 1.618. In addition, the family tree of honeybees also follows the familiar pattern. Even the microscopic realm is not immune to Fibonacci. The DNA molecules measure 34 angstroms long by 21 angstroms wide for each full cycle of its double helix spiral. Patterns can be seen everywhere. The Hungarian biologist and the French-American mathematician Benoit Mandelbrot showed how the mathematics of fractals could create plant growth patterns. As we've listened to the first part of the video, we knew what was it all about. In addition, mathematics, physics, and chemistry can explain patterns in nature at different levels and scales. patterns in living things are explained by the biological processes of natural selection and sexual selection. Studies of pattern formation make use of computer models to simulate a wide range of patterns. A tessellation or tiling is the covering of a surface using one or more geometric shapes, called tiles, with no overlaps and no gaps. Some special kinds include regular tailings, with regular polygonal tiles all of the same shape, and semi-regular with regular tiles of more than one shape. The patterns formed by periodic tailings can be categorized into 17 wallpaper groups. In botany, the term tessellate describes a checkered pattern. For example, on a flower petal, tree bark, or fruit. Flowers including the fritillary and some species of Colchicum are characteristically tessellate. Many patterns in nature are formed by cracks in sheets of materials. A regular tessellation is one made using only one regular polygon. A semi-regular tessellation uses two or more regular polygons. Triangles and squares, for example, form regular tessellations. A tessellation can be described by the shapes that meet at each vertex, or a corner point. In a tessellation, the shapes that appear at every vertex follow the same patterns of shape. A semi-regular tessellation is made up of two or more regular polygons. Some examples include hexagons, octagons, equilateral triangles, and dodecagons. Irregular tessellations consist of figures that aren't composed of regular polygons that interlock without gaps or overlaps. As you can probably guess, there are an infinite number of figures that form irregular tessellations. Have you ever thought about how nature likes to arrange itself in patterns in order to act efficiently? Nothing in nature happens without a reason. All of these patterns have an important reason to exist, and they also happen to be beautiful to watch. Check out examples of some of these patterns, and you may be able to spot a few the next time you go for a walk. A fractal is a detailed pattern that looks similar at any scale and repeats itself over time. Examples of fractals in nature are snowflakes, trees branching, lightning, and ferns. A fractal's pattern gets more complex as you observe it at larger scales. A spiral is a curved pattern that focuses on a center point and a series of circular shapes that revolve around it. Examples of spirals are pine cones, pineapples, hurricanes. The reasons for why plants use a spiral form is because they are constantly trying to grow but stay secure. A Voronoi pattern provides clues to nature's tendency to favor efficiency. Everything inside a cell is closer to its seed point than to any other seed. Other examples are the skin of a giraffe, honeycombs, foam bubbles, and the cells in a leaf. Symmetry is one of the mainstays of mathematics, and where math intersect with art and architecture. For physical objects, symmetry is built out of three basic types of transformations: rotation, reflection, and translation. In mathematics, with access to abstract spaces and higher dimensions, far more types of symmetry are possible. We will look at this in this post, as well as how we can use lack of symmetry as a warning or sentinel in both nature and society. The three types of natural symmetry are easier to understand with examples. The butterfly's wings are close to being mirror images of one another. The flower has eightfold rotational symmetry, and the graphene lattice can be moved onto itself by moving any one hexagon to another by sliding the sheet. The butterfly has only mirror symmetry. The flower has both rotational and mirror symmetry, while the graphene lattice has all three. These three types of symmetries can be mixed and matched, and they all refer to possible physical motions of asymmetric objects. Some symmetry, like that of crystals, arises directly from natural law, Living organisms shaped by evolution, however, arrived at symmetry by finding that the process of natural selection favored symmetry for some reason. With flowers, well, not all of them are symmetric. A symmetric flower is easier for a bee to spot as it stands out from the background, but some flowers take other paths, like looking something a pollinator would want to mate with or using garish colors to become easy to spot. The latter approach works with symmetry to make the flower more visible. There is another, very different, reason to favor symmetry. In a nutshell of all the discussion we have on this video, we come to realize that patterns make up a critical part of the natural world. As humans, we're meant to connect with these patterns on an innate, instinctive level. Knowing how beneficial patterns are, it makes perfect sense to build them into all aspects of design. As we reflect to it, we transpired all the patterns in our lives to go over what life above and beneath us. Simply say we live beautifully, and it's up to us to create great things we ought to get. This closes our video presentation. Please don't forget to click the subscribe button for more educational videos ahead. Hope you have a great day. Thanks for watching.